Okay, thank you for the introduction. As the title of the paper gives away, this is a paper about surface appearance about BRDF models, in particular diffuse rough BRDF. And I can hear people thinking, don't we have enough BRDFs by now? My answer will always be never, but on a more serious side, the motivation of our work is materials like those. So materials which are diffuse, which are clearly not Lambertian diffuse. If you look closer, most of them have some granularity, some porosity, and they have in common that traditional models, the one we have, they don't handle these kind of materials very gracefully. What we have in computer graphics is basically two different ways of simulating these things. So on one end, we have microfacet models. So a height field in every facet has a diffuse BRDF on it. And if you want to increase the roughness, what you do is you increase the roughness of the height field. The problem with this kind of formulation is, yes, it is simple, but the disadvantage is that these height fields, they become very unnatural because they start to have these spikes in the surface. Now, on the other hand, we can also represent materials volumetric. So recently, that's from 2021, there was a paper about Lambertian spheres, where you have spheres diluted in some kind of medium, disconnected with a Lambertian surface, and they can handle these kind of volumetric materials. What they cannot do is they cannot simulate solid surfaces. And now the question is, wouldn't it be great if we could have something in the middle, something which goes from one end to the other end? And this is exactly what we are presenting in this paper. So we have a diffuse model that can transition from traditional Lambert surface to Orenaya with low roughness, so a Beckmann height field, to the porous yet connected regime, and then to the Lambert sphere from 2021 in one single model. We base our work on two papers because this is what you do. You always build on other people's work. And in particular, we have one paper about microflakes and microfacet surface and how they are connected. From 2016 from Jonathan Dupuis and colleagues. And the other one is from last year, which presents a tool set of different techniques how to evaluate microfacets and microflakes. Going back to the first paper, so the main contribution of the first paper is that they were able to link microfacet and microflake theory, and in particular they derived the microflake model that exactly produces the multiple reflectance from the Smith micro surfaces. Great, but this is actually not what we really are very interested in this paper. What they also mentioned towards the end of the paper is that they present a theoretical concept. And so they propose to extend the NDF, which is normally specified in the upper hemisphere, to an entire sphere. And this means that the faces point down. And they argue that by doing this, you can create a continuous representation from materials which go from surface to volume. Now, the problem is that this requires accurate evaluation of the cross-section and the important sampling of the visible normal distribution. And they admit that they don't know how to do this with a full sphere within their framework. And so it's more a theoretical concept they present than an actual solution. Because, again, they could not evaluate it. This changed last year, because last year null scattering was introduced in 2023, also by Eugene. And so what the paper is doing, it's presenting a way to evaluate these full sphere NDFs. Quick description of the algorithm. It is inspired by distance sampling of heterogeneous volumes known as Woodcock or delta tracking. And what you do is you extend the ray into the volume, and then you sample a distance, you hit a particle which is there, and then you take the particle, you do disk sampling, so you shoot parallel ray onto the particle. You pick one randomly. Wherever you hit the particle, this is now your position and your microfacet normal. And then you take the microfacet normal and you take the distribution, you divide it by the majorant, which is the maximum of the NDF. And then you take this value as a threshold. And if your random number is smaller than the threshold, you have an actual collision there. So it's a real collision there. You take your microfacet normal and you use that one to calculate a new ray. Or if the random number is larger, then this collision never happened. You do not change the direction, you just proceed into the medium. What you then do is you do this again and again and again until you leave the medium, and that's it. Advantage, no cross-section calculations are necessary, so you circumvent this unknown thing we never knew how to do. The problem on the other end is that this is a stochastic process. It is very slow for low roughnesses because there is rejection sampling in there, and the lower the roughness, the more inefficient this algorithm becomes, which makes it more or less unusable in practice for low roughnesses. So our approach, our paper now is the first paper which combines these two ideas and puts them to a test. So similar to the 23 paper, we use von Mises-Fischer NDF as our full sphere distribution. Why this distribution? Well, it's because when you have a low roughness, it is very similar to the Beckmann NDF. And then if you start increasing the roughness, it becomes more and more isotropic, whereas the Beckmann distribution gets this rather weird shape. And the von Mises-Fischer becomes completely isotropic. What we also present in the paper is a remapping scheme of the roughness, because we want to have a linear roughness. So instead of going from 0 to infinity, like the Beckmann distribution, we go from 0 to 1 based on the total diffuse albedo, so that the change between numbers is as linear as possible. As said before, one problem with the Monte Carlo simulation is that it is too slow to run on the fly. So what we can do instead is we can use it as a basis to approximate and to build a closed form analytical BRDF, which captures the behavior instead. So the Monte Carlo simulation input is we have single-sided flakes. Single-sided in this context means that depending on the direction, the flakes will have a different property. The flakes are Lambertian, and we use the von Mises-Fischer NDF as our full sphere NDF. We put that one in the simulation. Simulation code is written in C++, and conveniently it is open source. So whenever someone wants to redo this work, go for it. Output is a lot of data. So we have 41 roughnesses simulated, and an average roughness takes around 10 minutes, but this means the average, so the low roughness takes a lot longer than 10 minutes, and the high roughness is shorter. The output of the simulation is now the input to our BRDF model. And everyone who has ever done approximations know that the secret to a good approximation is you reduce dimensionality. So the fewer dimensions you have, the better your approximation, no, the easier your approximation is. In our specific case, we don't try to fit the entire BRDF. We are trying to split it up in different bounces. Bounces, in our case, it's collisions, so how many interactions you have. And we simulate first bounce, second bounce, third bounce, and then everything which comes after, so 4+ bounces. We also extract the color from the simulation so that we don't have to have an extra dimension in the simulation. We keep that one separate. And then every component is itself approximated with a Fourier expansion, similar to what the Lambert sphere paper did to their formulas. The approximations themselves, I will not go too much into detail because they will be boring if I present them, because they're just formulas. But what it is interesting to know probably is that they are not polynomials fitted to data. They rely on prior knowledge about what these things should do. So in particular, they include concepts like an approximation to the VMF cross-section and the H functions, because we know these kind of things should be in there. So again, we don't want to spend the rest of the talk going through formulas, so I think it's better to look at the visualization instead, the output of what the formulas are doing. And in this particular case, we have roughness and albedo plotted in two different axes. What we can see is the majority of the energy is in the single scattering. And then due to the product of the color, so the thing we multiply into the collision, we can see that the energy becomes less and less. But for high roughness and high albedo, there's still a significant amount of energy in the multiple scattering contributions in there. We can also look at it from a more angular perspective. So first top row is the entire BSDF, and then we have split up the component again, going from left to right, different roughness. What we can see is that for the roughness 0, there is no energy in the additional components. This is not a coincidence. Our formulas, our approximation go back to 1 divided by pi for Lambert. And this means this is 0 in the additional bounces. And the further we go towards the roughness, the more we will have in the retroreflective peak. And we can also see this increase in saturation in the BSDF. The way we validated what we are doing, because we did validation, is that we validated with stochastic geometry. So what we did was we performed the brute force Monte Carlo simulation. We took parallel light reflecting from a cluster of stochastic geometries, and we compared that one with our BRDF. So in particular, image to the right, we have a roughness of 0.5 here, which is this porous but yet still connected regime where the traditional BSDFs have a hard time simulating that. And so going down from top to bottom, we make the radius of the sphere smaller, but we keep the density the same, which means that eventually we start losing all the features and get something like a BRDF. And this is what we then compare to our BRDF. Results look quite similar enough. And we also have the comparison for the individual bounces, so first order, second order, to see if everything is okay there. What the test shows is that the VMF, the von Mises-Fischer distribution, is not just convenient and not just something you can use to get this transition, but it also shows that we have something which is physically plausible for porous diffuse microgeometers. And this is also the paper, the first one, which shows that the full sphere NDF works and that it is not just an arbitrary concept. One side effect of including multiple bounces into materials is that they tend to become more saturated with increasing roughness due to the multiple scattering. This is a similar effect we can see on stochastic microfacets, and it is physically correct, so there is no question about this. But physically correct doesn't necessarily mean it is desired, especially it is not artist friendly. So if you want to paint a texture and the color you get out is not the color you get in, you are in deep trouble. So we also propose, in this sense, a remapping, which allows us to take an input texture under the hood, do some magic to convert it into something else, feed that one into the BRDF so that the result is the one which we expect. And it turns out that there is a very simple way of describing this effect of increased saturation. And we borrowed this formula from absorption increase, saturation increase of layered surfaces. And all we need to do now is to fit this eta to our roughness simulation data, and we get a remapping function. We tested it on spheres. So we have here a row of spheres in a white IBL, and the roughness is circularly changing from 0 to 1. What we can see in the top row where we don't have any remapping is that the roughness will introduce darkening, whereas when we do our remapping scheme, the colors stay more or less constant. Another nice things which these images show is that the darkening is not due to energy loss. So any kind of darkening we see is just pure to absorption. Even in the unremapped case, we still obey energy conservation. And we now go back to the rendered images. So what we can see is that the images, of course, change because we have a different BRDF model there, but the color impression is still more or less the same, which makes the authoring of textures a lot easier than if you would need to adjust for the saturation. Going further to the results, so on the left we have constant albedo, constant lighting direction, but we change the roughness. So we can see that for roughness 0, we get the Lambertian behavior with the dark edges, and then when we go towards higher roughness, we get this kind of fuzzy appearance we know from retroreflectivity, where we have the bright outline and the flat appearance. And the sphere on the right has also a constant albedo, but it has a textured roughness, so the little squares there, everything has a different kind of roughness, and the light which is spinning around. And what we can see there is that for some light configurations, independent from the roughness, it looks the same. But then for other lighting configurations, it looks different. And so different patches flare up at a different point in time. We also compared to Orenaya being the most often used diffuse, rough diffuse BRDF in production or in renders. Top row Orenaya, bottom row is the VMF diffuse material. What we can see is that the Orenaya model becomes darker. It does lose energy, so it is not energy conserving, but it also gets more of a dull appearance than the volumetric one we are striving to achieve. And in comparison, the VMS diffuse keeps the brightness and gets this fluffy appearance. And if we now compare to the Lambert sphere, so the pure volumetric model, we can see that the VMF diffuse material is almost identical. It is not entirely identical, so unfortunately the formulas, the approximations we have, they don't revert to the Lambert sphere model. Would be great if they would, they do not, so this is future research if anyone wants to do it. Our BRDF is of course not perfect, so it has a couple of limitations. First and foremost, it is not anisotropic. So it does not support anisotropy, and given that we work with approximative formulas, there is no way to just change the approximation and become an anisotropic model. So you need to go back to the simulation, you need to redo the simulation, you need to redo the fits to get an anisotropic model out of what we have. Then we also don't support perfect importance sampling. We use cosine sampling, which is also what Orenaya would normally do. In the grand scheme of things, that's not really super bad. I mean, of course, it's not perfect, but given that the BRDF has a kind of a uniform shape, you can get away with it. And then the third thing is, I pride myself to put as few formulas as possible in my talks. You can thank me later. But in this specific case, it's a little bit misleading because under the hood, there's a lot of stuff happening. There is many formulas and a lot of math which happens there. And this means that this is computationally kind of, well, heavy, which means real-time rendering, it is possible. As I said before, it just depends on how big your GPU is, if you can do real-time rendering or not. But our main target is offline rendering. This being said, it is possible, of course, to use a small MLP and fit something there, use that one instead for rendering, for real-time rendering. So it is proven that this works. If this is what you need, you can always go this way. And since we are not cruel people, we of course have the source code because we would not ask anyone to type all the formulas from the paper in their own source code. We provide a couple of implementation. We have a shader toy implementation, which is online right now, and a Mathematica implementation. Most likely there will be further implementations coming, something Mitsuba or Falcor, which is NVIDIA's renderer. And if you want to do the simulations yourself, I will point you to the Facet Forge, which is a set of tools Eugene presented last year at SIGGRAPH, which allows to computational efficiently evaluate these kind of materials. So with this, I would like to thank you for the attention.